In this video, we're going to start to understand the forces that hold molecules together that determine what state of matter they're going to be at room temperature, right? So for atoms that are near each other, or molecules, they interact through what are called electrostatic forces. And you can think of electrostatic forces as charges, right? So their electrons and protons will interact with each other. And it's really these intermolecular forces that determine, like I said, if it'll be a solid, gas, or liquid, right? And the strength of these forces really depends on the type of atoms we have, atoms or molecule. And in general, the stronger these attractive forces, intermolecular forces, the more they will resist moving and the more they'll be solid-like or liquid-like or gas-like. However, keep in mind, it is impossible for a material to have no motion. No matter what, molecules will always be vibrating. All right. So let's look at the strength of intermolecular forces then. Like I said, the strength of these forces determine what state it's in. So anything that has moderate to strong intermolecular forces or attractive forces, you're likely to be a solid or liquid at room temperature. And really, the stronger these forces are, you will also have higher boiling points or melting points of solid. There's also other factors that go into this, but you can think the stronger the glue is, these intermolecular attractions, these attractive forces, then the harder it is to go from a solid to a liquid, or the harder it is to go from a liquid to gas, because you have to break these attractive forces, and breaking these forces take energy. Now, let's actually look at why molecules are attracted to each other, have these forces. And it all has to do with charges, right? So intermolecular attractions are solely due to positive and negative ends interacting. So positive ion to a negative ion, or if you're dealing with polar molecules, positive end of a polar molecule and negative end of a polar molecule. And one type of this is called hydrogen bonding. And hydrogen bonding is really, really strong. That's why water behaves the way it is. And non-polar molecules also have temporary charges. And basically, the rule of thumb is the more charge you have, so -2, -3, so on and so forth, the stronger your attraction is. And the bigger the distance between these atoms, the weaker the attraction. Coulomb's law. If you go back to Gen Chem 1, we talked about Coulomb's law, and that also tells us this idea, but with equations. And let's look at this picture here. Here we have what is called hydrogen bonding. So this is a molecule of water, red's oxygen, and white is hydrogen. And this hydrogen is partially positive, and it's interacting with this oxygen, which is partially negative. And when you have a hydrogen and oxygen interacting like this intermolecularly, then you have a hydrogen bond. And let me just break down what the word intermolecular means. Inter means two different molecules. So interstate road goes between two different states. So an intermolecular force is a force between two different molecules. Now, keep in mind, even though this chapter we're talking about intermolecular forces, they are much, much, much weaker than bonding forces. So your covalent bonds, your ionic bonds are much stronger than these intermolecular forces are. And that's because these intermolecular forces are smaller in charge, and they're usually longer distances than your bonding, your covalent bonds and your ionic bonds. Right? So let's just look at one type of intermolecular force that all atoms and molecules will have, and these are your dispersion forces. They're called London forces or van der Waals forces. And basically, this is the idea that at any given time, any atom or molecule can have temporary charges. And the way to think about this is you have a molecule. And in the center of your molecule or an atom, you have your positive proton. And all around the proton is a cloud of electrons. At any given time, you can have electrons be at one side of your atom, and this will give you a partial negative charge. Well, on the other side of the atom, you'll have a partial positive charge, right? And so if one atom in your solution moves all its electrons to one side randomly, that'll become partial negative and partial positive. Then all the other atoms surrounding that one atom will respond in the opposite way, so that you'll have a negative next to a positive, next to a negative, next to a positive, so on and so forth. But these are temporary. They can change at any time, right? So here's a picture of what I'm talking about for helium. So helium, 2 protons, 2 electrons. So at one given time point, the electrons are evenly spaced out. Second time point, they're evenly spaced out. Third time point, just completely randomly, you have both electrons on the same side of the molecule. So this is now partially negative. Remember, this delta sign means partial, so partial negative. While the other side doesn't have any electrons, so it becomes partial positive. Now, when this happens, the other helium molecules around it will orient their own electrons, so the partial negative in atom 2 is lined up to the partial positive in atom 3, which means that atom 1. And so in atom 3, it will also create a partial negative to be next to atom 2's partial positive, so on and so forth. They will induce each other to have these temporary dipoles, right? And for these dipoles, the size and strength of these dipoles depend on a couple things. That is polarizability of the electrons and shape. So polarizability of the electrons is basically how many electrons you have. So the bigger the molar mass, the more electrons you'll have, which means the bigger electron cloud, which means when you become polarized, you'll have a bigger partial negative and a bigger partial positive, which leads to your stronger attractions. And in your shape, so remember, these atoms are physically interacting with each other. So the more surface contact you have, the bigger dipole you'll have, or the larger dipole you'll have, and the stronger attraction you'll have. And so let's actually take a look at these factors now with some data. For molecular size, we're going to focus on the noble gases, because the noble gases are all nonpolar. They all have a full octet, and they will increase from size very nicely. And what you can see is as the noble gases increase in size, their boiling point increases as well. That's because these gas molecules, for example in xenon, when they have an induced dipole, that induced dipole is much stronger than the induced dipole in helium, because xenon has a lot more electrons. And so the xenon molecules interact more strongly, therefore they have a higher boiling point because it takes more energy to separate the xenon molecules. So your rule of thumb to know, as molar masses increases, the number of electrons increase. Therefore, the strength of these dispersion forces increase. You want to know that trend right here. The second trend you want to know is the more surface area you have, the stronger the dispersion interaction. So let's look at N-pentane and neopentane. They have the same exact molar mass. They should have the same exact molar mass, maybe missing a couple hydrogens, but the same number of carbon. Neopentane is a sphere, and so when neopentane molecules interact, they only have one point of interaction. N-pentane is more linear, so there's more places for interaction. Therefore, N-pentane, since it has more surface area, has a higher boiling point, a higher melting point than neopentane. And if we just look at boiling point for these different gases, you can see as the gas gets longer, not only does their molar mass increase and therefore the number of electrons increase, the surface area of these molecules also increase, which leads to a linear increase in boiling point. So that's the second point you want to know. The greater the surface area, the stronger the dispersion interactions for these molecules. And that's it for this video. I'll see you in the next one.